Hi, this is a quiz review for related rates and derivatives of inverses. So questions 1 through 3, it says use the information below. It says let f be a differentiable function, and they give you this information. They say the function g is differentiable, and g is the inverse of f for all x. So what I like to do is not even look at what these questions are asking for. What I like to do is set up the chart with the given information. So I'll start off with f of negative 3 is 4. So if f of negative 3 is 4, the corresponding point on g, which is the inverse function, is 4, negative 3. And therefore, f prime at negative 3, they told us, was 2. So from this chart, we can figure out g prime of 4, which is 1 over 2. So g prime of 4 is 1 over 2. So that actually answers question 2. Next, I'll use this piece of information. F of 4 is 2, and we'll make a chart of that. Therefore, the point on the inverse function is 2, 4. And now we should include information about f prime of 4, which is negative 6/7. So g prime at 2, the corresponding new x value for the inverse, is the reciprocal negative 7 over 6. And that would actually help us answer. Oh, I'm sorry. You know what? This is negative 2. My bad. So this new x value is negative 2. So this is negative 2. That would help us answer this question. And as you see, we're out of information. We can't find g prime of 2. There's not enough info. And the reason is because we don't know an x value such that f of x is equal to 2. This was not given, okay? So there are your answers, 1, 2, 3, and most of you got these right in class. All right, number 4 is a little trickier. It says let f be the function defined by, why is that not working? Here we go. Defined by f of x is tan x minus secant squared x. It says if g of x is f inverse of x and g of negative 1 is pi over 4, what is the value of g prime of negative 1? So if we set up our little chart here, g of negative 1 is pi over 4, so that's a point on the graph of g, which corresponds to the following point on the graph of f. So they want us to figure out g prime of negative 1. But in order to do that, we're given more information about f, so I'd like to use f as the route to get the answer. We would need to find f prime evaluated at pi over 4. But first, we need to find f prime of x. So f of x is tan x minus secant squared of x. So f prime of x, the derivative tangent is secant squared. Derivative of secant squared, I want to rewrite this as secant x in parentheses squared. Chain rule, I have derivative stuff squared, which is 2 times the stuff times the derivative of the stuff. The derivative of secant x is secant x tan x. So actually, my derivative is kind of interesting. It's secant squared x minus 2 secant squared x tan x. Now we need to evaluate this derivative at x is pi over 4. So f prime at pi over 4 is secant squared of pi over 4 minus 2 secant squared pi over 4 tan pi over 4. Pi over 4 is 45 degrees, so I will draw a 45-degree reference triangle. 45, 45, 90. And the legs are 1, and the hypotenuse is root 2. So secant is the reciprocal of cosine. So that's hypotenuse over adjacent, which turns out to be square root of 2 over 1, or just square root of 2. But we need to square that. So secant squared of 45 degrees is radical 2 squared, which is just 2. So a few things happen. This secant squared becomes 2, minus 2, and so does this secant squared. Now we need tan. Tan of 45 degrees is opposite over adjacent, which is 1 over 1, or just 1. So this becomes times 1. And so we get 2 minus 4, which is negative 2. So that's f prime at pi over 4. That's not the answer. We wanted g prime, the derivative of the inverse at negative 1, take the reciprocal, negative 1/2. So the final answer to this question is negative 1/2. Seems like a simple question, but there's quite a bit of work to do there. All right, number 5 asks us to find the derivative of arc tan x cubed. A few derivative rules you absolutely need to know. The derivative of arc sine of x is 1 over root 1 minus x squared. The derivative of arc cosine of x is negative 1 over root 1 minus x squared. And the derivative of arc tan x is 1 over 1 plus x squared. In your packet, we carefully derived the arc sine and the arc tangent formula, and I gave you the arc cosine formula. So here we have arc tan of stuff. Derivative of arc tan of stuff is 1 over 1 plus the stuff squared. The stuff is x cubed, and by the chain rule, we need to multiply by the derivative of the stuff, which is 3x squared. So we get 3x squared over 1 plus x to the 6th. And that's a nice little final answer. X cubed squared is x to the 6th. All right, number 6 says we want to find f prime at negative 2 if f of x is arc sine of e to the negative 3x. So we have arc sine of stuff. So the derivative of arc sine of stuff is 1 over square root of 1 minus the stuff squared. And the stuff is e to the negative 3x. We must, by the chain rule, take the derivative of the stuff, which is e to the stuff. So the derivative of e to the stuff is itself times the derivative of negative 3x, which is negative 3. So altogether here, in the numerator of a fraction, I would have negative 3 e to the negative 3x over square root of 1 minus e to the negative 3x squared. We multiply exponents. When we raise exponents to exponents, we would get e to the negative 6x. And there would your final answer be. Number 7, we want the derivative of sine of arc cosine of x. So again, we're going to use the chain rule. Derivative sine of stuff is cosine of stuff. The stuff is arc cosine of x. Times the derivative of the stuff, and the derivative of arc cosine is negative 1 over root 1 minus x squared. Now, as we said, if we took this expression is interesting. It says, what's the cosine of the angle whose cosine is x? Well, if you think about it in terms of numbers, so the cosine of the angle whose cosine is 1. Well, the angle whose cosine of 1 is 0, and the cosine of 0 is 1. So what happens is you get what you started with. The cosines cancel, or the cosine and the arc cosine cancel, if you will, and you're left with what you started with. So the same thing happens here because they're inverses. So we just are left with the x. So this part is just x, and now we're going to be left with negative x over square root of 1 minus x squared as the final answer. Number 8, when the derivative of inverse tan of x, please also know that notation tan negative 1 means inverse tan. So I have derivative of tangent of stuff, which is 1 over 1 plus the stuff squared times the derivative of the stuff. The stuff is square root of x, so I need to come over here and take its derivative. Rewriting this as x to the 1/2, I want to take the derivative of x to the 1/2, which is 1/2 x to the negative 1/2 by the power rule, which is 1 over 2 root x. So I want to multiply by 1 over 2 root x. And now we can simplify this into one fraction. We would get 1 over 2 radical x times, in parentheses, radical x squared is just x, so I get 1 plus x in parentheses. And that's good for the answer. All right, number 9 says, consider the curve defined by this equation. We want to find dy over dx. This really should be something you can do virtually with your eyes closed. We're going to take the derivative with respect to x on both sides. So we have 3x squared plus 3y squared dy over dx equals 3 dy over dx. And the constant term goes away. So now we want to move all the dy dx's to the other side. I would do it this way. You could do it the other way, but then there's more moving that you have to do. So we get 3x squared equals 3 minus 3y squared, pulling out a dy over dx. And now we can divide by 3 minus 3y squared on both sides. So we get dy over dx is equal to 3x squared over 3 minus 3y squared. And since every term has a 3, we can divide by the 3. So we get x squared over 1 minus y squared. So there's our derivative. Part B says we want to write the equation of the tangent line to the curve at the point 2, 3. So here's our formula for the equation of any line. They gave us two parts. They gave us y minus 3 equals, we have to fill in the m, and we have x minus 2. M is going to come from the derivative. So in the last problem, we found the derivative to be x squared over 1 minus y squared. So the slope is x squared over 1 minus y squared. Whoops. And they gave us the values for x and y. So now we know the slope at the point 2, 3 would be 2 squared over 1 minus 3 squared. So 2 squared is 4 over 1 minus 9, which is negative 8. So the slope is negative 1/2. And there would be your equation of the tangent line. Part C is talking about finding all points on the curve such that the curve has a vertical tangent line. So you take the derivative, which is, what was it? X squared. Checking here, x squared over 1 minus y squared. That's the derivative. And we set the denominator equal to 0 because if you have a vertical tangent line, the slope is undefined, which means denominator is 0. So 1 minus y squared is 0 means 1 is y squared. Taking the square root and remembering that there are actually two solutions to this, y could be either plus or minus 1. Now, if y is positive 1 or y is negative 1, that could produce very different x values. So we go back to the original equation, which, if my memory serves me correctly, was this. And we're going to plug in y as 1. So we have x cubed plus 1 is equal to 3 plus 26, which is 29. We get x cubed is 28. And to solve for x, we could take the cube root on both sides. So x is the cube root of 28. And same thing here, except instead of y being 1, y is now negative 1. So we get x cubed. Negative 1 quantity cubed is negative 1 equals 3y, which is negative 3, plus 26, which is 23. Add 1 to both sides. X cubed is 24. Taking the cube root, we get x is the cube root of 24. So we end up with 2 points, one of which is the cube root of 28, comma 1. And the other point is the cube root of 24, comma negative 1. Part D asks us to find the value of the second derivative at 2, 3. So we need to take the first derivative, which was x squared over 1 minus y squared, and differentiate it again. This will give us the second derivative. This is a quotient, so we must use the quotient rule. So high is x squared, high prime is 2x, low is 1 minus y squared, low prime is negative 2y dy over dx. And so we have low d high, so that's 1 minus y squared times 2x minus high d low, which is a subtraction of a negative becomes a positive 2x squared y dy over dx over 1 minus y squared squared. Now we want to find this at 2, 3. So what I claim is that we've actually already found, if you notice, the first derivative is embedded in here. And we actually know that value from part B, because part B asks us to find the slope of this line, which is the slope of the tangent line at that point, which is identical to the derivative. So dy over dx is actually going to be negative 1/2, and C part B if you're not sure about that. Okay, so now I have 1 minus 3 squared times 2 times 2 plus 2 times 2 squared times 3 times negative 1/2 over 1 minus 3 squared squared. And we just have a lot of number crunching to do. This is negative 8 times 2 times 2, which is negative 32, minus, because we have minus, this 2 goes away with this one, we get 12, over 1 minus 3 squared is 8 squared, or sorry, negative 8 squared, which is 64. So we get negative 44 over 64, which if you care to reduce, you can divide both these guys by 4, and you would get negative 11 over 16 as a nice reduced final answer. Number 10, interesting question. Very similar to the ship question. Whoops, sorry. Mr. B sees an old friend at a concession stand at a football game and starts walking towards him. So Mr. B is walking due north. So this is B for me. At a speed of 5 feet per second. At the same time, the old friend who wants nothing to do with Mr. B speed walks across the field due west to get away from Mr. B at a speed of 7 feet per second. So here is the old friend who is trying to get away from me. Since Mr. B is hungry, he's always hungry, he continues to walk through the concession stand despite the fact that his friend is running away from him. So it says when Mr. B is 20 feet away from the concession stand and the old friend is 15 feet away from the concession stand, at what rate is the distance between Mr. B and the old friend changing? So we have to kind of identify what we want. And what we want is we want the rate at which the distance between the two guys is changing. So that's this thing. This quantity is changing. So I want dd over dt. We know the rates at which the men are walking. So we know dB over dt. This is where you have to be careful. I am walking toward the concession stand. So this distance, my distance away from the concession stand is shrinking. So my that rate of 5 feet per second must be negative. Critical. We also know that the friend is walking away from the concession stand, so his distance from the concession stand is increasing. So that rate should be positive 7. Okay. When do we want this all to occur? Well, we want this to occur when B is 20 and the old friend is 15 feet away from the concession. So now we want a relationship between all three quantities. Our old friend, the Pythagorean theorem, will do. And to introduce the rates, we're going to differentiate both sides with respect to time. So we get 2b dB over dt. Remember to use the chain rule here. Plus 2f dF over dt is 2 big D, big D over, sorry, dt. So now let's see what we know. We know, first of all, by the way, the 2's can divide out, so that just makes us a little easier. So B is 20, dB dt is negative 5, plus F is 15, times dF over dt is 7, equals, oh, we don't know big D at this point, so we're going to have to figure that out because dd over td is what we want at the end. So when B is 20 and F is 15, we flash freeze time. And so big B is 20, this is us 15, and you can use the Pythagorean theorem, or you can know that your triple says this is a 3, 4, 5 just multiplied by 5. So big D is actually 25. And now it's just number crunching. 20 times negative 5 is negative 100. Plus 15 times 7 is 105. That equals 25 d big D over dt. We get 5 is equal to 25 dd over dt. Divide by 25. And d over dt is actually, sorry, not 5, 1 over 5. And our units here, we're measuring the distance in feet. We're measuring time in seconds. Always use correct units. Alrighty, on to part B. Part B says, at what rate is theta, the angle between Mr. B's path and a direct path between Mr. B and his old friend, changing? When Mr. B is 20 feet away from the and his old friend is 15 feet away from the concession. Let me just draw the diagram There's the concession stand. Here is theta. It's already labeled for you in the diagram. So if you're not sure what theta is from the words, you can always go back to the diagram. This is all changing. Again, what we want is the rate at which the angle is changing. So we want d theta over dt when, we know the same rates of speed as before. We know that dB over dt is -5. We know that dF over dt is 7. When, same stuff, B is 20, F is 15. Easiest way to do this is to relate. We know everything about B and F. So easiest way to do this is to relate theta to B and F. And if you notice, opposite over adjacent is the winner. So that's tangent. So tan theta is equal to F over B. Now, what I said to make this a little easier was to cross multiply here. So we get B tan theta is equal to F. This is just to avoiding using the quotient rule if we can, which we can. So now we're going to differentiate both sides with respect to time. So I'm going to quickly come over here and just write a little product rule set up for myself. The derivative of B is dB over dt. The derivative of tan theta, you have to be careful here, is secant squared theta d theta over dt. Theta is a function of time. So now we could set this up. We would get tan theta times dB over dt plus b secant squared theta d theta over dt equals dF over dt. And now we want to solve for d theta over dt, so we have some stuff to plug in. So tan theta, secant squared theta. We don't know those at the moment, but we're going to use our when picture to figure that out. So here's theta. We know this is, this is 20, this is 15, this is 25. So tan theta is opposite over adjacent if you're standing at the angle. So tan theta, opposite is 15, adjacent is 20. This reduces to 3 over 4. Much easier to put the reduced version in. dB over dt turns out to be -5. Plus b, which was 20, times secant theta, or secant squared. Secant of theta, at this point, secant is hypotenuse over adjacent. So that's 25 over 20, better known as 5 over 4. But we need secant squared. So we'll just take that and square it. We get 25 over 16. So this becomes 25 over 16 d theta over dt, which is the guy that I want. That equals dF over dt, which is 7. All right, so now we have some just ugly arithmetic to do. We get -15 over 4 plus, this reduces to, let's see, 5 over 4. 5 times 25 is 125. Now this equation isn't terrible if you realize multiply by 4 and life is a lot easier because there's no more denominator. So I get -15 plus 125 d theta over dt is 28. Adding 15 over, we get 125 d theta over dt is 43. Divided by 125, we get d theta over dt is 43 over 125 radians per second. Calculus is done in radians. If you wanted to convert this to degrees, you could multiply by 180 over pi to see how many degrees this would be. All right, next problem. We have our friend the right circular cone. The right circular cone is being filled with water. Sorry, I'm just trying to make this go away. Sorry, a right circular cone is being filled with water so that the volume of the water in the cone is increasing at a rate of 8 pi cubic centimeters per second. Let me just get this out of the way also. It says when the height of the water in the cone is 2 centimeters, at what rate is the radius of the water changing? Include appropriate units of measure. So we want to find dr over dt. We know that the volume is being, because you're pouring water into the cone, so you're pouring it in at a constant rate of 8 pi. We would like to find, we want to figure this out when the height is 2. So I wrote this in on the sheet. I don't have it on the smartboard, but the volume formula for cone is this. Now, what's so obnoxious about this is that the radius and the height are changing. But good news, if you understand triangle proportionality, you can make this problem much simpler. So if you notice, the diameter is 18, so the radius is 9, okay, and the height is 6. So the big triangle is in a ratio of 9 to 6. So the little triangle, the r over h triangle, also has to be in that ratio. So 9 over 6 equals r over h. We get 9h is 6r. Now notice, we want dr over dt, so I would like to take the h out of this. I don't want h around because I want to find dr over dt. So I'm going to try to solve this for h. Divided by 9, we get h is 6r over 9, which is 2/3 r. So now my volume formula looks a little nicer. My volume formula is 1/3 pi r squared times 2/3 r, coming from a little analysis that we did with the similarity in the cone. So we get v is actually 2/9 pi r cubed. And now we can take the derivative with respect to time on both sides. We would get dv over dt is the 3 drops down, and so you get 2/3 pi r squared dr over dt. And now we have some nice things we can fill in. We know that dv over dt is 8 pi. We have 2/3 pi times the radius, times dr over dt. We don't know the radius, but we do know the height. So if the height is 2/3 times the radius, multiplying by the reciprocal, 3/2 times the height is the radius. So the radius is 3/2 times 2, which is 3. So another advantage of knowing that relationship is that it enables you to actually get the radius when you're given the height. So next up, we have 8 pi is 2/3 pi times 3 squared. 3 squared is 9, and 9 divided by 3 is 3. So we actually get 2 times 3, which is 6 pi. So this actually works out fairly nicely. 8 pi is 6 pi dr over dt, divided by 6 pi. And dr over dt is the pi's go away, and 8 over 6 reduces to 4 over 3. Units are critical. Radius would be measured in this case. Our lengths are being measured in centimeters, and our time is in seconds. So this is centimeters per second. All right, not so bad. Part B says, when the height of the water is 2 centimeters, at what rate is the exposed surface area of the water changing? So our want is a little different. It's the exposed surface area of the water, dA over dt. Our know is still dV over dt is 8 pi. But notice, when the height of the cone is 2 centimeters, we just found dr over dt to be 4 over 3. So we know that from part A. That could be useful. We'll have to see. We also, the when is still the same. So when the height is 2, we also knew that the radius was 3. So we want dA over dt, so we're going to use the area formula. And if you think about what the surface area of a cone is, it's the circle that's exposed. So area is pi r squared. It does not depend on the height of the cone. So now we're going to differentiate both sides with respect to time. So we get dA over dt equals 2 pi r dr over dt. So it was very nice to know dr over dt at this time because dA over dt is written in terms of it. So dA over dt is 2 pi times the radius, which is 3, times 4/3. So this comes out very nicely. The 3's go away. I get dA over dt is 8 pi. This is an area now, so it's centimeters squared per second. Measuring heights in centimeters? quick, I'm just forgetting. Yes, we were. So there is our answer. And one more question. Whoops. Backwards. It says, when the area of the exposed surface area of the water is 25 pi centimeters squared, at what rate is the diameter of the exposed surface area of the water changing? So now, we still know dV over dt was constant no matter what time we were at. We want, this time, the rate at which the diameter is changing with respect to time. If you think about something for a minute, though, the diameter is twice the radius. So let's say the radius was expanding at 4 centimeters per second. The diameter would be expanding at 8 centimeters per second. So what we really want is 2 times dr over dt. And real quick, if you know the diameter is 2 times the radius, if you took the derivative on both sides, this is exactly what you would get. That's what we want. When has changed. So that rate, this rate dr over dt is 4 over 3, is only good at this when. So that's not going to be any good anymore. I'm not going to put that in the no column because our when has changed. The area is 25 pi. Now, if the area is 25 pi, area is pi r squared. It's a little good to do this at the beginning right here. So r squared is 25. So the radius is 5. That's when we know this is occurring. Now, this is tricky because the only thing that we know is dV over dt is constant no matter what time. We're going to have to go back to the volume. Now, if we remember from part A, the volume was 2/9 pi r cubed. Okay? Volume was 2/9 pi r cubed. And the reason we have to go back to the volume is because this is the only thing, this rate stays constant no matter what. Okay? So we're going to have to differentiate with respect to time here because that's going to introduce dV over dt, which is the quantity that we know. So we get dV over dt is 2/3 pi r squared dr over dt. dV over dt is 8 pi equals 2/3 pi times, we know 5 squared dr over dt. We have 8 pi. 5 squared is 25 times 2 is 50. So I have 50 over 3 pi dr over dt. And keeping in mind, if I get dr over dt, I just have to multiply by 2 to get the answer that we want. Because we wanted the derivative, we wanted the rate of change of the diameter. So the pi's go away. We can multiply by 3 over 50 to rid ourselves of the 50 over 3. So we end up getting 24 over 50 equals dr over dt. This reduces to 12 over 25. But translating this to dd over dt requires us to multiply by 2, which is 24 over 25 centimeters per second. And that's the final answer. That's definitely a trickier question to figure out, that you need the volume formula that we got in part A, as opposed to surface area, because it's the when that's tricky. The when really gives you, the when in this case generates a radius. So this is definitely a harder question. And we're done.